my understanding is, and we'll soon know more about that, is that about 15 billion years ago, or at least before that, there was no time at all. So time really just started at some finite point, but we'll be told about that perhaps. Anyway, this morning's talks consist of, there are 4 lectures, and the first lecture is by Professor Avishai Galyam. Avishai Galyam is a professor at the Weizmann Institute of Science. He received his PhD in 2004 from the School of Physics and Astronomy at Tel Aviv University, and he received his postdoctoral training as a NASA Hubble Fellow at Caltech in California. His current research is focused on understanding the physics of cosmic explosions of stars and other violent astrophysical phenomena and their implications for our understanding of stellar evolution, of cosmology, and of the origin of chemical elements in the universe. But today, he will talk to us about the beginnings of time, the genesis of time. His talk is Measuring the Genesis of Time and Matter. Avishai, thank you very much.
So my task is to talk about the beginning of time, the genesis of time and matter. And I will also try to connect it with other timely subjects, subjects that are timely in that they are connected to time, and also that are timely because they are connected to the current frontiers in our understanding of the universe. So when people think about Genesis in modern cosmology and astrophysics, we always think about the beginning of everything in the Big Bang. And this is an illustration that describes the evolution of the universe from this Genesis Big Bang until now, and I will slowly go over it and talk a bit about what is described there. It's, of course, an illustration. This part contains very little observations, but the rest of the talk, I will try to hang the insights I provide over real observations. So the context of this talk would be more connecting to what we can really measure from the universe, rather to the more philosophical questions that, of course, can also be asked about these issues. So, in modern general relativity-based understanding of the universe, time and space are connected with each other, and they are all part of the matrix of coordinates with which we describe the universe. And these coordinates were created during the Big Bang, which means, as Kobi has said, that before the Big Bang, since this was before the beginning of these coordinates, there was nothing, including no time. And therefore, the question of what happened before the Big Bang, before describes a relative term of time, has no meaning. Those of you who pursue mathematics know that it is quite easily actually to define such a metric that has a finite beginning and does not involve a continuous a line of time, even though for us, based on our everyday experience, it is quite difficult to imagine something before which there was nothing. And the question of before does not even exist. So we have evidence that the universe started in a big explosion that we call a Big Bang that happened in a certain point of time, and we can measure the time it took for the universe to expand since that point to now, and it is approximately 14 billion years. So your approximation, Kobi, was good to about 10%. Following that explosion, there was a period of very rapid expansion, which we called inflation. And during this period, the universe was opaque to light. It was so dense that rays of light would interact again and again with particles, eventually with electrons, and could not propagate very far. And therefore, the entire universe was very homogeneous. But during this expansion, the universe became rarer and rarer, and therefore it became eventually transparent. And when the universe turned from opaque to transparent, the light that was until then locked in this interaction with matter, escaped and can travel, or could travel, or could decouple from matter. And this light we see today, and it provides direct evidence and something we can concretely measure and tells us about the properties of the material shortly after the Big Bang. And this is how this measurement looks like. And now we switch from a cartoon to a real measurement of the universe. This is a map produced by a satellite launched by the European Space Agency called Planck. And the property that is described in this map is the temperature of the sky measured extremely accurately as a function of the position on the celestial sphere. So if I were to point out the horizontal axis of this ellipse would be our galaxy. And every point here is either above or below the disk of our galaxy. And the other coordinate is the angle with respect to this pole. So in each point of the sky, this satellite very carefully measured the exact temperature that we measure. Why is there a temperature to these points of sky? These are the photons from the light burst from the Big Bang. The photons escaped, they were extremely hot, but the universe has greatly expanded since then, and this light cooled to a temperature equivalent to about 3 degrees above the absolute zero. 3 degrees is the average temperature, and what we are seeing here are the fluctuations above this or below this average. And these fluctuations are at the level of a few times a millionth of a degree. Right? These are very small fluctuations. And because of that, it needs a very well-controlled and accurate instrumentation to measure them, but this is possible, and you can see here the results. And you see that the temperature of the universe is not homogeneous across the sky. It's very nearly homogeneous, but not exactly so. And there are significant variations from spot to spot. Now, in principle, this in itself strikes you not as a very revealing measurement. However, the history of the universe up to and after this evolution is encoded in this pattern of hot and cold spots. And you can actually predict how much difference you typically see between points of sky as a function of the distance between these 2 points. And this is what we see here. This is the same measurement displayed in a different way. So here we see a graph showing us the power or how correlated are 2 points in the sky when we measure the temperature in 2 points on the sky as a function of how distant they are from each other in degrees. And you see below on the left side, there are points that are far away on the sky, let's say 90 degrees apart. And on the right, points that are very close to each other, less than or much less than a single degree. And you see that the difference between 2 points on the sky on average as a function of the distance between those 2 points is very far from constant. There are typical scales on the skies. And these scales are predicted from cosmological models. And as you can see, they are measured very accurately from the map of temperatures that we saw before. So the points here, the red points, are the measurements, including their errors. And you can see that these errors are very small. And they are very well fit by these models. This means that the parameters of the models, which tell us how the universe evolved since the beginning of time in the Big Bang until now, are quite well constrained. And that means also that the universe must be expanding. This is something we already knew, but more so that it is currently accelerating. I return to this plot here, and let me show you what I mean by the fact that the universe is accelerating. So here we see the passage of time. And this is the total age of the universe, 13.7 billion years. And this scale shows us how the scale of the universe grows. We see that it grows very rapidly at the beginning. This is acceleration. And then it grows more or less at a constant rate. It means that the velocity of the expansion of the universe is more or less constant. But here, relatively recently, it is again accelerating. The fact that the universe is currently accelerating, the typical distances between galaxies are growing, and the rate of growth is going up and up with time is the biggest puzzle in current physics. And the reason for that is that it cannot be explained by any physical force that we are aware of. The scales are so large that the only physical force that has any power over such distant scales between galaxies is gravity. And as you all know, gravity is a force that only pulls. So between any two physical bodies, there is a physical force of gravity that tends to pull them together. This means that there is no force that can cause the universe to accelerate and expand, because this requires a force that causes objects to move apart from each other. And we don't know about any force like that. So this means either there is some very new force that acts on very large distances that we have no explanation for, or that we do not understand properly gravity. And gravity might itself also have a repellent manifestation that we do not understand. Either way, this is something that we measure empirically, and we have no theoretical understanding of at all. So this is quite a dramatic mystery, and in my opinion, definitely the most important and puzzling physical problem that we currently have. Okay, now this is something we measure on the very largest scales of the entire universe. Can we test this locally? And the answer is yes. And the equivalent local measurement of what we just described, what we learn from measuring the entire temperature of the whole universe as we see in all directions, the local measurement, and when we say local in astrophysics, we mean our local environment, which means the nearby galaxies to us. This is still a timescale of hundreds of millions of light years. Okay? This is very not local to to regular people, but for astrophysics, this is local. And by the way, a short time in astrophysics, million years, for example, is very short time. The way to measure it locally was actually the basis of all cosmology. And this was done by Hubble, the famous American astronomer, almost 100 years ago. And this is by measuring the correlation between how far away an object is from us, let's say a nearby galaxy, what is the distance to a nearby galaxy, and how far away it is receding from us. So the correlation between the distance of galaxies and their velocities with respect to us, and all of these velocities for galaxies that are not really next to us, are always away from us, right? The universe is expanding. Galaxies are moving away. This is the original plot from Hubble, and it shows that indeed, if you look at more distant and more distant galaxies, the velocities go up. So there is a strong correlation, and the slope of this correlation is called the Hubble constant. It's actually a parameter, so now we call it the Hubble parameter because the value of this parameter changes with the age of the universe. The current value of this parameter is called the Hubble constant. The Hubble constant is quite approximately 1 over the age of the universe. So if we take our best measurement of the Hubble constant, h0 there, 1 over that will give us more or less 14 billion years, which is our estimate of the age of the universe. There are corrections to this statement. So if we measure the cosmology using this method, it will give us some local idea about the age of the universe. And this is how we do this. Now, in order to do this measurement, and this has been a focus of astronomy for the last century or so, we need to do something that is very simple, and that is to measure distances. Now, on Earth, distance is one of the things that are easiest to measure, right? There's no problem to measure the distance between myself and the wall over there, or even the distance between here and some point on the Earth, to great accuracy. And this is the simple reason is that we can just go from one place to another and do some sort of measurement. Of course, in astronomy, the distances are huge. We cannot go to the other side of the distance we want to measure and put some object over there. And in addition to that, the problem is that most sources of light we see in the universe, we do not have any information about them except for the amount of light that reaches us from those distant sources. Now, if we imagine that we have a strong source of light and a weak source of light, as we measure it here using our devices, the reason for the difference in the amount of light we get could be two. One is that one of them is really a strong source and the second is a weak source. But the other one is that they could be the same sources, but one of them could be close to us and a lot of light would reach us, and the other one could be much more distant, and therefore little light would reach us. And if we have no other information about the source, we cannot distinguish between those two properties. So we cannot distinguish a nearby source from a distant source, just from measuring the light from the source. So how can we overcome this problem? So the way that astronomers and mathematicians for 200 or 300 years now have been doing that is demonstrated in this plot and is called a parallax. Luckily for us, the Earth is rotating around the sun for many reasons. One of the reasons, okay, thank you, yes. One of the reasons this is good for us is that if we are observing a star, let's say this star, on the background of other stars in our galaxy, and if we are observing, let's say now, in the winter, we will see it in this direction. But half a year later, when we go around the sun, and we do the same measurements of the star, we will see it with a slightly different background. Now, this picture is very much exaggerated. In reality, the difference between those two lines is very small because the stars are distant, and the distance from the Earth to the sun is much smaller. But still, this change in angle can be measured. And through trigonometry, if we have this angle and we know the distance between the Earth and the sun, we also know the distance between us and the star. This simple method is called parallax, and we can use it to measure stars in our galaxy with greater and greater accuracy. The accuracy depends on our ability to measure this small angle here. Okay, so we need to have devices that allow us to measure the location of stars relative to other stars very accurately, and this we keep improving. And what Hubble discovered is that some of those stars emit light in a way that depends on time. So they are not constant sources of light, but rather time variable. The amount of light they emit is variable, and this is illustrated here. These are real observations of such a star. And some of those stars, called variable Cepheids, they have this very useful property, which is that the variability that we measure is proportional to the luminosity of the star, how much light the star emits absolutely. So if we measure this variability, which we can do without knowing the distance to the star, we know how much light the star really emits, and that gives us a measurement of the distance, because we can now separate the two options, whether it emits a lot of light but is far away, or whether it emits little light but is closer to us. So by measuring the amount of light as a function of time, we measure the distance to such stars, and we calibrate this relation using parallax measurements. And then the big discovery of Hubble was that you can find such variable stars not in our galaxy, but in other galaxies. You can measure the way that the amount of light that they emit changes with time, and this will give us a measurement of the distance from us to a distant galaxy. And with that discovery, Hubble discovered several interesting things. The first thing, of course, was that these things that you see in the sky that look like nebulae are actually not clouds of gas in our galaxy, but rather other galaxies very far away. Now it sounds trivial to us, but then it was not trivial at all. And you can imagine, if you think about this as a time in analogy of geography, it is like realizing that the Earth is suddenly bigger by billions of times more than you thought. Right? It's a bigger revolution than the Columbian Revolution of the discovery of the Americas. So suddenly the universe is huge. It contains many galaxies, and they are very far away. And in addition, what Hubble immediately did was plot the distance of these distant galaxies as a function of the velocity he measured between the light from that galaxy and us. And these velocities are measured through the Doppler effect, which for lack of time I will not illustrate here, but this is a property of light that allows us to measure the relative velocity between a source of light and us. And he showed that the universe is expanding. And this was Hubble's great discovery. And now, which is illustrated here, sorry. And now we can use this method in conjunction with other distance estimation methods to build a distance ladder, okay? So we can measure now the distance between us and very distant galaxies, even galaxies where we cannot see individual stars. And the way to do it is through a ladder that used to have many stages and now has mainly 2 stages. You measure the distance to nearby galaxies using these variable stars, and then you choose not any galaxies, but galaxies in which something special happened, and this something special is that a star in that galaxy exploded as a supernova. Let me stop for a second and say this. Some stars in the universe become unstable and explode. These are dramatic explosions. These stars emit in a few days or a few weeks the amount of energy equivalent to the entire energy that the sun will ever emit, okay, in billions of years of its existence. All of this is compressed to a few weeks. So the amount of light per unit time is huge, and because of that we can see such explosions to great distances. Now, if I happen to know the distance to a galaxy in which one of those explosions happened, and these explosions belong to a certain type which has the property of being what we call a standard candle. So the amount of light emitted in the explosion is more or less constant. I can now measure the distance not only to this galaxy, but to all other galaxies in which I found similar explosions. So that allows us to measure distances halfway across the universe using this ladder of local calibration, calibration of nearby galaxies, and then calibration of distant galaxies using 2 methods. And using that, 2 teams of scientists conducted such measurements of the expansion of the universe across time. So in astronomy, when we look farther away, we look back in time, right? Because the velocity of light is constant, the farther away we look back in time. It's like a time machine. And in 2011, the Nobel Physics Prize was awarded to these 2 teams for measuring, using Hubble's ideas, the cosmology of the universe, and indeed it shows that the universe is rapidly expanding and accelerating. So everything seems well. By measuring the cosmic microwave background, the light from the explosion of the universe, we learn that it is accelerating. For measuring locally and then more distantly using distance estimators, we see that the universe is accelerating. It seems like, at least empirically, we have a complete picture. But the situation is actually not like that, or at least not like that entirely. If you measure the actual value of Hubble's constant from the measurement of the microwave background using Planck that I showed you before, and if you measure it locally using these measurements that have recently been completed by recent collaborators, you see that there is a difference in the value you get. And because both measurements are very accurate, this distance, even though it does not seem large, if you check how discrepant are these measurements, you find that the discrepancy is actually quite significant. We measure in statistics this discrepancy in units of Gaussian sigma. And so in those units, this is 3.3 sigma, which is about the chance that this would happen randomly is very small. It's certainly less than 1%. This is quite surprising, and some people would say troubling, because we have 2 very accurate measurements, both of them very well based on physical ideas that we understand, and still there is discrepancy. And empirically, I would say this is one of the great puzzles right now in cosmology. I don't have a solution. I would have been glad to show you now the brilliant solution to this problem, but I don't know it. However, instead, I will show you an idea about how to get such a solution. And this will lead us to one additional timely subject, which is gravitational waves. So, what are gravitational waves? Let's just stop just for a second and explain this. Let's think about electromagnetic waves like light. This is something that we are all familiar with, because if there were no light here, you couldn't have seen me. So, what are electromagnetic waves? Let's assume that we have an electric charge. Let's say an electron, it has some electric charge. If this electron moves in space, the field of electricity around it changes with time because the source is moving. And if it is moving periodically, the field, the electromagnetic field, will change periodically in space and time and will propagate as a wave. This is how you create electromagnetic waves. If you have a radio antenna, inside you have electrons moving periodically, and this creates a radio wave that will propagate in space, okay? So if you have a moving source of field, of power, you will get a propagating wave, and these waves propagate at the speed of light. In exact analogy, if you have a source of gravitational field, let's say a massive body like the sun, and if this body was to move in space periodically in time, you would create a field of gravitational waves that would propagate in space with the velocity of light. This was calculated by Einstein about 80 years ago, and mathematically it's very simple to calculate, and there's no argument about the idea and its manifestation. Two problems. One is that gravity is much weaker force than electromagnetism. So the power in these waves is very, very weak, and it's very, very difficult to measure them. That's one point. The second point is I just described to you something that is much harder to do empirically, which is to move the sun periodically with time. Of course, this is not something we can do. So what in the universe can cause something as heavy as the sun to move in space periodically? So of course, the answer is another star. If we have two stars, and they move around each other, like the Earth is moving around the sun, but now we have two stars like the sun, and they move around each other. If we look now at one of them, it means that one of them is moving periodically in space. It is creating a gravitational wave that changes with time, and this gravitational field will create a gravitational wave that will propagate in space. Okay, so we have, if we were to find two stars moving around each other, we will have a source of gravitational waves. In fact, this is not rare at all. About half the stars in our galaxy are not single like the sun, but rather are in binary systems revolving around each other. However, for regular stars like the sun, gravitational waves are too weak to measure. We need something even stronger. What could make this stronger? The force between two bodies, the gravitational force, depends on the masses of the bodies. So we already went for very massive stars, so that's good. But it also depends on the distance between the two bodies. The closer the distance, the stronger the force by a power of 2. So we want to have these stars closer to each other in order to move around each other with great acceleration, and that will create stronger gravitational waves. Now, the closest distance we can put two stars like the sun next to each other is when they actually touch each other. If we try to push them any closer, they will just merge and create a single star, and then we have no waves. Turns out that if we put two stars like the sun almost touching each other, we still do not get enough power in gravitational waves to be able to measure them. So how can we overcome this? We need stars that are as massive as the sun, or even more massive, it will be even earlier, but smaller, so that we can push them closer and closer together. Not we, but nature might help us and create systems where they are very close to each other, revolve rapidly around each other, have very strong forces, and create gravitational waves. What sort of stars could have these properties that they are extremely massive and yet very, very small, or occupy a very, very small space in the universe? There are two such systems of stars that we know. One of them are called neutron stars, and I will talk about those in a second. And the other ones that are the smallest and most densest objects in the universe are black holes. Black holes are the mathematical representation of matter that has been compressed to such small distances that the escape velocity from the concentration of matter is equivalent to or greater than the speed of light. It means nothing can escape. Indeed, after decades of efforts, scientists have been able to measure 2 years ago gravitational wave signals coming from systems of binary black holes rotating around each other, and this is illustrated here. These are how these systems rotate around each other. Because they lose energy in gravitational waves, they fall towards each other and eventually merge. This is the comparison of models and measurements of such events. And on this discovery of gravitational waves, this year's Nobel Physics Prize was awarded. Now, The problem with this measurement with black holes is that they emit nothing except for gravitational waves, and therefore I cannot measure the distance directly or actually the velocity of these systems because I don't know exactly where they are. If, on the other hand, this emission comes from two neutron stars, which are very dense stars that are almost black holes but not exactly, so they have material that is as dense as the nuclei of atoms, and those neutron stars merge, we can get a signal of gravitational waves from which we can accurately measure the distance, and there is some electromagnetic emission from which we can measure the velocity using the Doppler effect. And this was done for the first time this last August, a few months ago. And from that, we can get a measurement of Hubble's constant. And if we have something like 30 events, and so far we have one, we would be able to measure directly, without the cosmic distance ladder, Hubble's constant to about 1% accuracy. And this probably will give us an answer whether there is real problem in our cosmology and the age of the universe or not. One thing I haven't time to explain because we run out of time, but this also relates to how we create matter in the universe, and this subject we'll have to postpone, I guess, for the next meeting about matter rather than time. So I will skip this and just leave you with our conclusions and leave some time for questions. Thank you very much.
Thank you very much, Avishai. You took us from 13.7 billion years ago to just a few months ago, and now, even now, we've run out of the few minutes of time. But the other minutes, there are a couple of minutes for questions. Are there any questions? I've got one question. Right at the beginning, you showed a fit of some model to the temperature variations in the. You showed a fit of some model to the temperature variations in the universe, and it was a wonderful fit.
Right.
And the line was supposed to be a theory. Now, how many adjustable parameters?
7. There are 7 parameters in that model.
7 parameters?
Right, yes. And there are, as you saw, many, many tens of measurements. So it's extremely well constrained. Yes.
I see. 7 adjustable parameters.
There is a question from the gentleman over there.
Question? Yes, there's a, yes? Would you like to ask a question? Yes, please ask. Yeah.
Oh, thank you. Thank you. In physics, there are 2 concepts of time. One is the measurement of time, and the other one is the flow of time, which is a variable that has no beginning and has no end. And therefore, the blanket statement that there was no time before or afterwards contradicts the meaning of the variable that we use in all the equations. So, what's your comment on that?
Right. So if I can rephrase your questions. So in physics, we use time, we measure time, but also time is a variable that the flow of time is intimately related to things like thermodynamics, for example. To define thermodynamic concepts, we need time, and that variable in thermodynamics cannot have a beginning because before that thermodynamics will not be defined. And I think this is actually the answer, right? That because time started at the Big Bang, you indeed cannot define thermodynamic concepts earlier than that time, which I think is actually quite reasonable because almost all physical measurable parameters that we can define go to a singularity. They become either 0 or infinity at the Big Bang. So it is not surprising that thermodynamic theories, which are effective theories of ensembles of many particles, are not well defined at these conditions.
Thank you very much, Avishai.